Okay, so applications of double integrals. We've already seen one application of double integrals, computing volumes. Another geometric application is defining areas of surfaces, and we're actually going to do that next. This is going to be, we'll do that next. In this section, we're going to explore physical applications such as computing mass, electric charge, center of mass, and moment of inertia. Okay, and these physical ideas are also important when applied to a probability density function of two random variables. But I'll let the probability application go, but feel free to look at it if you like. Okay, so let's go ahead here. Okay, so density and mass. So how many remember that density is defined as mass over volume? How many remember that maybe in middle school or high school seeing that definition? Density is the mass of an object divided by its volume. Okay, Kino remembers that, and Madeline remembers that. Excellent. And you know what we're going to do here? What we're going to do here is we're going to consider a lamina with variable density. Okay. Now, one moment here. One moment. Let me just check something real quick here. So a lamina is defined as a thin layer or plate of material. That's what a lamina is defined as. So we can define the density of a lamina as the change. It can be defined as mass over area. Okay, or delta M over delta A. Well, it's mass over area instead of mass over volume. I'm going to be very simple how I explain things here. Now, you know, there's your figure 1, okay? And if you want to define the mass over the entire lamina in figure 1, okay, let me bring it down. Well, okay, what you could do is being that density, they're defining it as mass over area for a small, you know, near a point. That means that mass would be equal to density times area. So density is mass divided by area. Therefore, mass is density times area. Okay, and that's what you have here in this little Riemann sum here. Well, it's a double Riemann sum. Why is it double Riemann sum? Because if you want to find the full mass over that lamina, you got to sample points over the entire lamina, and that means x changes and y changes, right? So you can so that you can move around in the xy plane. So that's going to require then a Riemann sum to approximate the mass. The mass would be approximately the double Riemann sum of every little piece of mass at the different points. That would be the density at a point times the little area at a point. Now, what is this double integral then naturally going to become? What will it become, class? That double integral. I'm sorry, that double summation. As you take the limit, as you take more and more points in the lamina, what's the double Riemann sum going to turn into? Well, okay. I was thinking the double Riemann sum would turn into a double a double integral. That's the answer I was looking for there. And indeed, that's the case. So therefore, we obtain the total mass of the lamina right here. Okay, we obtain the total mass of a lamina. The total mass of the lamina is equal to the double integral over the region D, over the lamina, where your integrand is your density function, Okay. Are there any questions on that? All right. if you're good with that, we will move on. Let me just see if there's something I wanted to mention here. They do, remember in calculus 2, they talked about also centers of mass for a plate, and you came up with formulas there. You came up with some formulas. These formulas are going to they're just, you're going to get different formulas to find the center of mass for a lamina or a plate. Yes, you do need rho. You do need the density function. Yes, you do need that. The rho there, that looks like a P, but it's not quite a P. It's a rho. And in WebAssign, you have to be careful, right? When you put in answers, to pick the right symbols, right? No, rho is not an A. Well, rho, we don't really treat rho, even with spherical coordinates, we treat rho as like a radius. It stands for a radius, but no. In this case, the rho stands for a density function that varies depending which point you're on the lamina. Okay, all right. So, well, all right. So now, physicists, they mention here, physicists also consider other types of density that can be treated in the same manner. So if you have an electric charge over region D, and the charge density is given by the lowercase sigma at xy, that's just a notation, then the total charge is given by that. How many, I don't know, has anybody seen that in another class? I don't know if you would have, because, you need calculus 3, you need multivariable calculus. But Charles has seen it in physics too. Okay, excellent. Okay, wonderful. So, all right. So they have examples here. I really just want to go over the formulas. Your homework, every homework problem for this section is going to have like a help aid to it. So I want to just sort of go over the theory a little bit and go from there. So you have then moments about axes. So if we want to find the center of mass of a lamina, in other words, think of a lamina with different density. You want to find the point on the lamina where it would balance. If you were to put the plate, the lamina, on your finger, on vertical finger, where would it balance? Okay, it's how many have like balanced a basketball on top of their finger? How many have had that experience where you balance a basketball on top of your finger? You spin the ball around, but it's balanced on your finger. Or how many have seen that? How many have seen that? Maybe, I'm sure you must have seen that. I'm trying to give you a, sure. Well, so in order for the ball to spin that ball on your finger, you have to, I want to be a little careful. It's not quite that simple. But what I'm trying to say is the basketball is balanced on the finger. Think of a plate and taking your finger vertically and balancing the plate on your finger. What point on the plate is going to go on top of your finger? Okay, you have to find the right point. Well, it would be the exact center if you knew, if it were a disc, if it were a circle of constant density, the exact center would be that. But yeah, that's right, Ian. We're looking for the fulcrum point. That's exactly right. So the fulcrum point will consist of coordinates. Hold on here. Let me. The fulcrum point would consist of coordinates given by x bar and y bar. So you have to find moments about the x-axis and the y-axis in order to get that center of mass, or the fulcrum point. So the mass about the x-axis is defined as the double integral over the lamina of y times the density. Okay, so the how far away. I want to say this the right way. How far points are on the lamina from the x-axis affects the center of mass, right? Okay, with respect to the x-axis. Okay, so that's why the y variable is the variable that tells you how far a point is away from the x-axis. So that's why for the moment about the x-axis for the lamina, you have a y times the density. Now, similarly, the moment about the y-axis, okay, for that, you would have double integral of x times the density. So again, if you have a point on a lamina and you're, how does that affect the center of mass about the y-axis? Well, how far is the point from the y-axis? That's going to be an x distance. And so, there's your moment about the y-axis. Am I explaining this? Is this making sense? Is this... Okay. Take a little time to absorb. Sure. All right, Gordon, very good. All right, Hinu. So, yeah, just trying to give you an intuitive feel. So, Hinu, the M and N in the sigma notation, it just means that, like, remember in section 12.1 when you were approximating double integrals and you had you split the area up into 4 regions and like n was equal to 2 and n was equal to 2, or you could split the region up into 6. You could split the region of integration up into 6 little rectangles, and you'd have, maybe m equals 2 and n equals 3. It's the same kind of thing. But if you let m and n go to infinity, you're sampling an infinite number of points, and that's going to get you the exact moment about the y-axis. Excellent. So, these formulas, you're just going to apply these formulas in your homework, okay? And you know that you'll have access to these formulas on exam 3, okay? You'll have access to those formulas. So now let's see what the center of mass would be then. Okay, the center of mass. Okay, so here they say the lamina balances horizontally when supported at its center of mass. Okay, and they have a figure 4 here. I think I'll show that figure 4. There we go. Okay, so you see the x bar, y bar, that coordinate is the center of mass for that lamina D. Okay, so the center of mass then, the way you find that is you take your moments about the x-axis and y-axis and divide that by the mass, m. Okay, that's how you find your moments. I'm sorry, that's how you find the coordinates for your center of mass, the x bar, y bar. Okay, so this is are there any questions on that? Okay, so I'm not going to really, when you do your homework, you're just applying those formulas. Juliana's feeling good, Huda's feeling good. Okay, let's talk about moment of inertia. Let's talk about moment of inertia. Let's go there, okay? So, moment of inertia, okay, about the x-axis. So let me just see here. Let me just highlight this. One moment. Hold on, everybody. Okay, so the moment of inertia is defined as the product of a mass of a section and the square of the distance between the reference axis and the centroid. But what moment of inertia does is it measures the extent to which an object resists rotational acceleration about a particular axis. Now, I don't want to get too deep into the weeds here, okay? I don't want to get too deep into like, in terms of physics and things like that. But I think it's important that you do some problems with the moment of inertia, because you'll likely see it in another class. Charles, what class did you see moment of inertia in? You told me you saw it. Was it Physics 2? Physics 1. Okay. All right. Well, all right. So, thank you. So, okay, you have a moment of inertia of a lamina about an x-axis. Okay, and that's how it's defined. The double integral over the region D, the lamina of y squared times the density dA. Okay, and then you know, and again, y is the distance from, you know, a particular particle to the x-axis, right? And then you have a moment of inertia about the y-axis. Okay, how many has anybody seen these definitions before in another class? Charles, did they do that in Physics 1? That, or was that, I mean, they have, okay, all right. So, all right, very good, very good. Well, you know, so now, you know, you're getting the calculus perspective. Okay, well, no problem. Well, at least, you know, if you do a few of these problems, you'll be better prepared, you know, for when you do see it. Okay, excellent, excellent. So now you also have a moment of inertia about the origin. Okay, about the origin, and that's going to involve x squared plus y squared. Okay. Okay, and Charles saying you had to derive certain laws in his physics class. So, well, it just tells you how important this material is. When you do your homework for section 12.5, these are the formulas that you will be referring to. Okay, and again, on your next exam, you will have access to those formulas. Okay, you don't have to memorize them. Are there any questions at all? Any engineer could look up those formulas if they needed to, so I think it's reasonable. Are there any questions? Okay, very good, very good. All right, well, let me stop the recording.